Researchers have found compelling evidence of multiple mineral-forming events just below the planet's surface on Mars. Sulfate minerals exist with different amounts of water in most regions on Mars that allow us to understand how water moved around the planet, which is key to understanding its past habitability. However, it is not fully understood yet how or even when these minerals formed. Recently, a new way to measure the internal crystal structure of these minerals directly in the rocks was found, which was thought to be impossible on the surface of Mars. To find the evidence, scientists used data from NASA's Perseverance rover. The rover has been exploring the red planet's Zero crater since February 2021 and picking up samples of rock, hoping to find signs of ancient microbial life. They adapted a new analytical method called X-ray backscatter diffraction mapping to work with the rover's planetary instrument for X-ray lithochemistry instrument, which helps to study the internal chemistry of Mars rocks. Diffraction mapping uses patterns to create maps of the properties of material, including where crystals are found. With this method and the rover's data, scientists could determine the orientation of the crystal structures of the Martian minerals, providing a fingerprint showing how and when they grew as well as in what conditions. In part of the Zero crater known as Shenandoah Formation, two generations of calcium sulfate minerals formed beneath the surface. Calcium sulfate is a naturally occurring mineral that is commonly found in gypsum, a mineral used in brewing beer and other products. This discovery highlights the diversity of environments that existed in the Shenandoah Formation's history, indicating multiple potential windows when life might have been possible on Mars. Since landing at the Zero crater in 2021, Perseverance rover has completed 4 science campaigns: the crater floor, fan front, upper fan and margin unit. Now Perseverance is beginning its fifth campaign named Northern Rim because its route covers the northern part of the southwestern section of Zero's rim. Over the first year of the Northern Rim campaign, the rover is expected to visit as many as 4 sites of geologic interest, take several samples, and drive about 4 miles. The Northern Rim campaign brings completely new scientific riches as Perseverance roves into fundamentally new geology. It marks the transition from rocks that partially filled the Jezero crater when it was formed by a massive impact about 3.9 billion years ago to rocks from deep down inside Mars that were thrown upward to form the crater rim after impact. These rocks represent pieces of early Martian crust and are among the oldest rocks found anywhere in the solar system. Investigating them could help understand what Mars and our planet may have looked like in the beginning. This view of the rim of the Zero crater was taken by Perseverance rover as it reached the end of its long climb from the crater floor. Not visible here is Witch Hazel Hill, a scientifically significant rocky outcrop that is 1500 feet down the other side of the rim that Perseverance is headed toward. Once there, the rover will spend about 6 months exploring the area. Scientists are excited to explore the region outside of the Zero because the rover will encounter rocks excavated by a monster meteor impact that formed the crater an estimated 3.9 billion years ago. These rocks could not only be early Martian crust but among the oldest rocks found anywhere in the solar system. Springtime in the south polar region of Mars is a season of exciting activity. The thick coating of carbon dioxide ice that accumulated over the winter begins to sublimate as the sun rises higher in the sky and warms the ice. Sunlight penetrates through the transparent ice and is absorbed at the base of the ice layer. The gas that forms as a result of the warming escapes through weaknesses in the ice and erupts in the form of magnificent geysers of gas and dust. What makes this image interesting is the changing directions of the fans left behind by the geysers, indicating that the winds blew from different directions at the time the geysers erupted. Winds from the southwest produced the dark fans at both ends of the image, whereas northwesterly winds dominated dust deposition in between. Local topography probably played a role in altering the wind direction, as this image traverses a trough in the south polar layer deposits, which may have funneled winds downslope along the length of the trough.